Alright guys, so this is 11.3. So for this lesson we're going to review combinations this time. And combinations are actually pretty easy. It's very similar to permutation in that you are still trying to figure out how many ways things can be arranged. And you are using the entire group. But the difference is it doesn't matter the order in which you do it. So for example, ironically, the combination lock that you guys probably have seen before. So this is what I'm talking about. Let's say you've probably seen this. I'm not a good artist, guys, so you're gonna have to forgive me for doing a bad job. It looks like this and has like numbers here, and you're supposed to spin this in 3 different numbers, right? It's called the combination lock. That's actually technically a permutation lock if you really want to be specific, because suppose I knew the 3 codes. Let's say the codes, I don't know, were 1, 2, and 3. Okay, if that were even possible, I would have to put it in a specific order for it to unlock. So it's not a combination, it's really a permutation, because a combination would say any as long as I use 1, 2, and 3 in any order, it would open. That's a combination. So that's what the idea of combination is. I think there's, I'm not sure, like 30 numbers to choose from, so it'd be like 30, choose 3 out of the 30. I'm not even sure how many numbers are in a combination lock, but whatever. The idea is that the combination, the order doesn't matter, excuse me. Permutation, the order does. That's the main difference. Also, for combinations, you don't do combinations of the entire class, because then that's just the entire class. That's it, just a group of one giant group. We're gonna make groups of 5, group of 5. So that's a combination of 5 people. It doesn't matter who got picked first. You're on the team, right? That's the idea. That's the idea of a combination. So let's see what it says here. Can you distinguish between a permutation and a combination? For each of the following problems, determine whether the problem involves one. Okay, so let's see. A yogurt shops 12 different color assortments, sorted flavors. Sorry. One of its items in a bowl consists of 4 flavors, each of a different flavor. How many such bowls are possible? Let me read this one more time. A yogurt shops 12 assorted flavors. One of its items is a bowl consisting of any 4 flavors, each a different flavor. How many bowls are there possible? I guess it doesn't matter the order, because if you put vanilla, I guess it depends how picky you are, right? If you put vanilla first and then chocolate, and then I'm assuming like what others can you put? I'm not even sure. Strawberry and then blueberry. It doesn't matter the order as long as you have those 4 flavors, right? So I'm gonna say it's a combination. Again, unless you're very picky and it has to be first, but you know, you've seen people like that in Starbucks, right? First do this, then this, and this. Okay, so that's a bad example. Let's see what it says here. A bowl including 4 flavors be formed with 12 distinct flavors. The order in which the 4 flavors are put on the board is irrelevant. Okay, so yeah, I figured. Different order of flavors does not change. I don't like this example, but I get the idea. I would rather have said I'm going to pick a group of 3 people for my team, and everyone's going to be the same position. No one's going to have a different rank. So therefore, that's more of a combination, right? Let's see the second one. Medals were given at a race. Okay, boom. As soon as you talk about first, second, third, these are ranks, right? That's it. This is going to be a permutation. I'm not even going to read the rest. So, let's see. For each example, for each of the following problems, determine whether the problem is one involving permutation or combination is not necessarily to solve it. Okay, so we're not going to solve it, just going to figure it out. All right, A. So how many ways can you select 6 free DVDs from a list of 200? This is a combination, classic combination, because it doesn't matter which order you get the DVD. You're going to get the DVD no matter what, right? So if you pick Mission Impossible first or last, you got the Mission Impossible movie, which is a great movie, right? So it's irrelevant whether you picked it first or last. You still got the movie. So that's a definite combination. In a race, I can tell you right now, it's probably permutation. Let's read it. There are 50 runners and there's no ties. Ooh, that's a big one. How many ways can you get first 3 finishers to come in? Okay, that's a permutation. Oh, permutation. Sorry, I was thinking, how do you spell that? Whatever, my handwriting is bad enough. So, permutation. Okay, let's see. C. The order in which you selected DVDs does not matter. This is the answer. This is weird. Why would they put... Okay, so anyhow, this is the answer. I was right. It is combination. Good. And D, order matters. Permutation. Okay, good. So that was easy. Number 1 here. For the following problem, determine whether the problem is one involving permutations or combinations. Let's see. how many different 4-letter passwords can be formed from the letters A, B, C, all the way to G if no repetition letters are allowed? This is a clear permutation. This is like a combination lock, right? It actually matters the order in which you put it. So if your password is, how many? 4? A, B, C, D, and it doesn't matter the order, then you're going to guess it really quickly, right? But if it's a particular order, if it's in that particular, it has to be A, B, C, D, and then it works. Not, B, A, C, D or something like that. It has to be specifically in that way, then it's going to work. So it's a permutation. Clear example of a permutation. So, see the next part. All right, back to combinations. Okay, we're going to talk about the formula for combinations. So the formula for combinations is almost like permutation, but then it divides one more time by r factorial. You notice that's the only difference. Okay, the reason for that is for the repeats, right? You don't want to repeat the same groups again and again. So if you have, let's say 3 people are in group A, and they can switch 3 factorial different ways, right? Because it's groups of 3. I don't want to repeat them because that's already a group. Like, it doesn't matter the order I picked it. So I divide by that repeat. So that's why that r factorial is down there. So let's see what it says here. For example, in a card game of Go Fish, a person is dealt with 5 cards from a standard deck of 52 cards. The order which the 5 cards are received does not matter. How many different ways can... Okay, so there's 52 cards. And it doesn't matter the order, but you need to get 5 cards. So it's just 52 combination 5. And we're just going to do 52 factorial over 52 minus 5 factorial. And then because we have groups of 5, we don't care about that group itself in all its variations repeated is irrelevant to us. So we divide by 5 factorial as well to cancel that group, right? It's elf. It doesn't have to be repeated. Combinations don't care about order. So repeats divide out. So then we're going to get, let's see what they did for us. I'm not going to work all that out. We're going to get 52 over 47 times 5. They worked out the 52. They realized 47 factorials cancel. The 5 factorial, they left it there. They just did this in their calculator, I'm assuming. End up getting almost 2.6 million. So another example. You walk your dogs as a part-time summer job. You have a client with 5 dogs. You only walk 3 at any given time. So there you go. So you have 5 dogs to choose from. 5 choose 3. Now remember, it doesn't matter. As long as you walk the dogs, it doesn't matter who goes first. Not like one dog has an issue, has to go right away, if it's too hot. Now, if that is the case, then of course it's permutation. But I actually have to keep reading. How many different combinations are there if you walk 3 to 5? The order selecting dogs does not matter. Okay, there you go. That doesn't matter, so it's a combination. So again, 5 factorial. Let me make this a little neater. 5 factorial over 5 minus 3. Wait. Factorial. Divide by 3 factorial, excuse me. We have groups of 3. So that's it. And then we're going to get, that's easy for me to do, 5 times 4 times 3 times 2 times 1 over 5 minus 3 is 2. So 2 times 1, 2 factorial, and then 3 times 2 times 1. So these cancel, and then this doesn't matter. And 5 divided by 4 is really 2. So it's 10, right? 5 times 2 is 10. That's simple enough. All right, so this is the last. Okay, so this is the very last example to work with this section. You volunteer to pet sit for your friend who has 7 animals. How many different pets combinations are there possible if you take 3 pets of the 7 at a time? Okay, so 7 combination 3 makes perfect sense. They plugged into the formula, they worked it out, and then getting 35. Easy. So there's 35 different ways that he would have gotten 3 pets out of the 7 if the order didn't matter, right? So let's do the last one. An election ballot asks voters to select 3 commissioners from a group of 6 candidates. And how many ways can this be done? I'm assuming commissioners are all the same, like ranking. So we're going to say 6 combination 3, which is 6 factorial over 6 minus 3 factorial. But then we have a group of 3. We don't care about that group repeating itself. So we divide that repeat away. We're going to get 6 times 5. Well, 6 minus 3 is 3 factorial, right? So I'm going to stop it there. And then the bottom should be 3 factorial times 3 factorial. At least one of them cancel out. So we're going to have 6 times 5 times 4 over 3 times 2 times 1. The 1 doesn't matter. And then, so check this out. 6 divided by 3 can be a 2. And 4 divided by 2 can be a 2 as well. So it's 2 times 5 times 2, that's 20. There are 20 ways that can be done. And that's it. That's it for chapter 11.4. No, sorry, this is 11.3. Yes, 11.3. I'll see you guys for 11.4.